near the video there. I'm not going to read through it completely, but we're going to go over the gist of it. What we're first going to do is take the word problem and formulate it as a model, as if you would do this on paper, but I'm just going to do it on a text editor here. And then I'm going to take that IP and plug it into Excel and you solve it using Solver. So the gist of this word problem is that I have a farmer and he produces apples and pumpkins, and he wants to sell these apples and pumpkins at a farmer's market. He has two options for a farmer's market. He can go to Troy or he can go to Schenectady. He cannot go to both because we're saying they're on the same day. The two farmers markets have setup costs to set up a stand at either location. So $500 for Troy and $400 for Schenectady. We're assuming this is a one-time gig. He's just thinking for this one day. The two stands also have different space constraints. There's 700 units of space in the Troy stand and 500 units in the Schenectady stand, where the different products that he is trying to sell, the apples take up 1 unit of space and pumpkins take up 3.75 units of space. Here we say that the farmer assumes everything he brings to his stand he's going to sell, and he sells them at different prices based off of his location, so therefore his net profit is different. So for an apple, in Troy he earns $2, and in Schenectady he earns $1.75. Similarly, for a pumpkin, he earns $3.25 in Troy and $2.75 in Schenectady. He can't just sell one product. He must sell apples and pumpkins. Therefore, we constrain it to say that 75% of the items in his stand you cannot have more apples than 75% of the number of items, and similarly for pumpkins. Here, the farmer wants to maximize his profits. So just looking at this, one would think, what decisions are we making? One, we're making a decision of what farmer's market to set up the stand in. And then we're also making a decision of how many apples and how many pumpkins should I put in my stand and sell at the location. So setting up a stand would allude to a binary decision variable, an x1 or x2, saying, yes, I set up a stand in Troy, or yes, I set up a stand in Schenectady, meaning x1 is Troy, x2 is Schenectady. Then you would also think, hey, I'm selling apples and pumpkins. I would have a decision variable for the number of apples I sell or put in my stand and the number of pumpkins I put in my stand. However, those decisions don't work. So if you pick the wrong decision variables, it's going to make things very hard to model. So in this case, if I only have two decision variables, one for the amount of apples I sell and one for the amount of pumpkins I sell, I can't factor in that I sell, or the profit I earned is different by location. So for example, if I had y1 equals the number of apples I sell, the amount I earn from this is dependent on the location. And so we need to expand this further to say the number of apples I sell in Troy, or the number of pumpkins I sell in Troy, and similarly for Schenectady. So we're going to take this and plug it into, let me make this all white before, plug it into a model here. So our first thing is we need to have decision variables. So like I said before, I want decision variables x1 binary that equals 1 if the farmer sets up a stand in Troy and 0 otherwise. Also, I'm going to have x2 equals 1 if the farmer sets up a stand in Schenectady and 0 otherwise. Also, like I alluded to and talked about, we cannot just have two decision variables for the number of apples and pumpkins that are sold. We need to expand this out to 4 in order to incorporate these extra separate parameters by location, as in the cost or profit that I earn by location. So here I'm going to have y11 equals the number of apples in Troy, meaning the number of apples I put in my stand and ultimately sell, because everything I bring I sell. And also y12 equals the number of apples I bring to Schenectady. So here 1 means apples, and the second 1 or 2 means either Troy or Schenectady. Then I have two other decision variables. Y21 is the number of pumpkins in Troy, and Y22 is the number of pumpkins in Schenectady. So now we've appropriately designed our decision variables. This is very critical in when you're modeling, is to fully capture what you need to decide and what level of detail. So here we decided that just capturing the level of detail of the number of apples I sell is not enough. I need to expand that to say the number of apples I sell in Troy. So now I look back to the write-up, and here I remember that I want to maximize profits. And profit I get is from selling apples and pumpkins, but also I have to incorporate subtracting off the amount I pay in order to set up the stand. So here in my objective function, I'm going to set it up here. I earn $2, if we remember here, I earn $2 for apples in Troy and $1.75 in Schenectady, and then $3.25, $2.75. So here, I earn $2 from selling apples in Troy and $1.75 in Schenectady, and then the same here for pumpkins in Troy and pumpkins in Schenectady. A lot of people want to incorporate these X1 and X2 decisions when you factor in the amount you earn here for apples that you sell in Troy. That won't work. So if I was going to multiply X1 right here, one, that makes it a nonlinear objective function, which we don't know how to handle yet. And we're going to constrain these variables, these y11 and the rest of my y variables, so that they're going to equal 0 if I don't set up the stand in that location. So here we're just going to incorporate the profits. Also, we need to subtract off the amount I pay based off of location. So I pay $500 in Troy or $400 in Schenectady. So there's our objective function. Now we need to look at what constraints do I have. So in the write-up, starting from the top, it says he has two options. He can either set it up in Troy or Schenectady, but he can't set it up in both. Further, we don't say that he has to set up a stand at all. If he realizes it's not profitable to sell, then he's not going to set up a stand at all. So with this, we're going to say that the decision to set it up in Troy plus the decision to set up in Schenectady is less than or equal to 1. It's not strictly equal to 1. That means he would have to set up one or the other. It's less than or equal to 1. Further, we can't set it up in both, meaning 1 yes for Troy and 1 yes for Schenectady. So what's another constraint here? Another constraint is the space amount. Here we have 700 units in Troy and 500 in Schenectady, and the apples and pumpkins take up the same space in either, 1 unit and 375. So with that, I'm going to include a constraint here that says this, so the number of apples, the space that my number of apples takes up, 1 unit times the number of apples, plus 375, the space that pumpkins take up times the amount of pumpkins I have, is less than or equal to 700. However, if I don't set up the stand in Troy, I don't get 700 units. So I would want these values to be forced to 0 if I don't set up a stand. So essentially, I would want this as two constraints. If I set up in Troy, I want this to be less than or equal to 700. And otherwise, if I don't set up in Troy, I want these two values to be less than or equal to 0. We can't incorporate these if-then statements into our solver. We want to incorporate them into an equation. So for this particular case, to capture that, all I'm going to do is multiply times x1. Here I say x1, if x1 equals 1, then I get my real constraint, that these values are less than or equal to 700. I can't exceed the capacity of the stand. Otherwise, if this equals 0, then these values will be forced to 0, which is exactly what I want. I don't want to bring any apples to Troy if I don't have a stand there. And so we do the same thing for my stand in Schenectady. Here I look at the number of apples, the space that the number of apples take up, 1 times the number of apples plus the space that the pumpkins take up in Schenectady has to be less than or equal to 500 only if I set up the stand in Schenectady. So there's our capacity constraints for our stand. Now, so looking further at the word problem, we've already incorporated these costs, the profit earned, into the objective function. We don't have to constrain that all. The last constraint that we see here is that the number of apples cannot exceed 75% of the total number of items. So we're not worried about space that they take up. We're worried now about the number of items. We want a variety of items. We don't want them all to be apples. So because we've separated our decision variables by location, we're going to need different constraints factoring this in by location. So first here, I'm going to look at Troy. I'm going to look here at the number of apples in Troy has to be less than or equal to 75% of the total number of items in Troy. So we've already constrained these y variables to be 0 if I don't set up a stand in Troy through this constraint here. So I don't need to worry about if I've set up a stand there anymore. I only need to worry about the 75%. So here's the total number of items in Troy and apples. I'm going to do the same thing here for number of pumpkins. I'm going to say the number of pumpkins here is less in Troy is less than 75% of the total number of items I have in Troy. Then I'm going to do the same thing here for Schenectady. Looking at the first one is the number of apples in Schenectady has to be less than or equal to 75% of the total number of items in Schenectady, and similarly here for pumpkins. So now I have every constraint satisfied. Although I need to make sure I do not forget to have types of variables. Here I have x1 and x2, which are going to be binary variables. They're 1 and 0. And also I have 4 variables here, which are going to be integer variables for apples in Troy and apples in Schenectady, similarly for pumpkins. We're not going to allow them to bring partial apples or partial pumpkins. So with that, I make sure not to forget that I have these constraints here, which are integer and greater or equal to 0, as well as binary variables here, x1 and x2, which are in the set 0, 1. So that concludes our IP. And I'm just going to change it slightly to make it a little easier to put it into Excel. It's going to be the same exact equivalent IP, except for I'm going to move, here I see that I have different variables on the right-hand side. So I'm just going to move these over to their appropriate column on the left-hand side. So this constraint here, I just transform, I subtract off 700 and put it on this side. Here I subtract off 500. And for these 4, I just subtract off their appropriate value and put it onto the left-hand side. So these 2 IPs are equivalent, it just makes it a little cleaner and easier to put into Excel. So now I have my full IP. I'm going to go over to Excel and want to put this and solve it. I have to model my decision variables, objective function, and constraints. So here I have an Excel document. I'm going to just take this whole model and put it in row by row. So Professor Sharkey has showed something similar, but this is a nice way, if you have your model formulated like this, it's an easy way for you to always be able to solve it. It doesn't matter if it's IP, it doesn't matter if it's an LP, it's just an easy way to formulate it. So here I have a max, and I have different coefficients of my decision variables. So here 2, 1.75, 3.25. So I'm going to just incorporate this. I have 2, 1.75, 3.25, I think it's 2.75, minus 500, minus 400. Let me double check that. 2, 3.24, 2.75, minus 500, minus 400. So essentially what I'm saying is that this column here will be y11, this is y12, y21, y22, x1, and 2. And so this is our objective function. Here are the coefficients, so 2 of y1, 1.75 of y2. Then I'm going to have a constraint here. I'm just going to put in my constraints exactly how I see it here. I have all zeros except for a 1 on x1 and a 1 on x2. So here 0, 0, 0, 0, 1, 1. And here I'm saying this has to be less than or equal to 1. And I do the same thing for all of my constraints. So 1, and then 3.75 and minus 400. So this is 1, 3.75, so minus 700. And these have to be less than or equal to 0. I'm just going to fill this in with zeros if it wasn't present. And so this constraint here, I have 1, 3.75 minus 500 on the opposite of the values in Schenectady. Fill this in with zeros where the variables were not present in that constraint. So here I have the first 3 constraints done. Now I need to do the next 4 constraints. So here 0.25 and minus 0.75 and just the opposite for the next constraint. So here I have 0.25, this was minus 0.75. These were not present. And then this was minus 0.75, 0.25, 0, 0, 0, 0, 0, 0, 0. So you'll see this is a nice pattern to go and put into Solver when you have any program. So again, I have similarly the 0.25 minus 0.75, but for my Schenectady variables. Just make sure you maintain the signs correctly when you put this in. This is minus 0.75. These were 0. Now I'm going to insert a column here because I want a way to calculate these. So right now I'm not multiplying these by anything. So I'm going to store here my decision variables because right now they're not decided. I want to tell Excel that this is where I'm going to store them. So I'm going to store my y1 in this value, y12 here, so on and so forth, for my 6 decision variables. I'm then going to use whatever values that these assume to calculate the objective function. So whatever value it solves for in y11 has to be multiplied by 2, and then this has to be multiplied by y12, so on and so forth, in order to calculate the objective function. So I'm going to calculate those values here. So I'm going to use sum product, which is essentially this times this plus this times this, but it just makes it a little easier to put into Excel. So I'm going to first put it in without locking any rows. So here I have the sum product of this row times this row. For this one, I know that it's going to be the sum product of this row times this row, because essentially I'm multiplying 0 times whatever values these assume, and then I just want 1 times whatever x1 is and 1 times whatever x2 is. So if I was to copy this down, so just Control C, copy this down into this cell without locking it, you'll see I've moved down a row here, but also down a row here. However, I don't want to move down a row here. I want the true decision variables. So that is why we lock rows. So here I'm going to lock this row 10, which can be done by F4 $ or F4 $ on Windows and Command T on a Mac. So here I've locked in that row corresponding to my decision variables, because I'm always going to use this row, but I want the top row, this blue row, to increment down as I copy it. So now here, when I copy and paste, you'll see that I have the right thing. I have this row here and my row of decision variables because I've locked that in. So now I can just copy these down and get the right values. So this here is taking this value, 0.25, times whatever y11 assumes, plus 0 times y12, so on and so forth. And so it will be easier here to put into Excel that these values are less than or equal to these values. So now I'm ready to enter it into Solver. So I'm going to go to Solver here, and hopefully you can see this box. Here my objective function is going to be evaluated in this objective function row. I want to maximize, and my cells that are changing here are these yellow variables. I just had done it before, so I'll delete the constraints. So my changing variables here were these yellow things I've highlighted as yellow. That's where I'm storing, that's what I'm deciding for. If you need to highlight two rows, so let's say I stored my y1 variables over here and then my x1 variables over here, or for whatever reason you need to select two ranges, you can select the one range, put a comma, and then select the next range. So now I have my objective function max and my decision variables. I need to add my constraints. So the way I've set it up here, it makes it really easy. I'm going to take this column here and say that it is less than or equal to this column here. And so I factor in all of my constraints with just those selections. Now I need to define the type of decision variables I have. So if we remember here, my y variables are integer, which I can do instead of the less than or equal to, I just select int, and I add that. And then my x variables were binary, and I add those. So going here down the constraints here I'm saying my y variables are integer, my x variables are binary, and then I factor in all the constraints. These are less than or equal to that. I want, if you have an older version of Excel, you might need to say that all of my variables are greater or equal to 0, especially for the integer ones. But I can accomplish that. But this checkbox here, and I want to make sure I solve using simplex, then I just click solve. And it might take a little bit longer for integer solutions. Here a solution has been found. And let's look at this solution. Here I have an objective function value of 458. My values here are binary, 1 and 0, and I only set up one location. I set it up in Troy. And also here I see that I have integer amounts of apples and pumpkins. Also, all of these other constraints are satisfied. Here we see this constraint right here, which was for the capacity at Troy. I'm at capacity, so I cannot raise these values any higher, because here I have that the amount of apples, the space that they take, plus the amount of space that pumpkins take, minus the capacity, exactly equals 0 here. And it has to be less than or equal to 0. So therefore I have no excess capacity space-wise. I do have excess capacity in the number of apples that I could take. So here these say that I'm not exactly at 75% of either of them. And so this is our solution we found. It satisfies the integrality and the binary decision variables, and it's just a nice way to formulate any programming model. Again, feedback is appreciated. Hopefully, I realize this is cutting close to the deadline for the homework, but hopefully people are able to still gain some insight from it, either for the homework or for the midterm. Okay, thanks.